So we've seen that smartphone cameras, and for that matter professional astronomical telescopes, are fundamentally limited in two ways. One is the wave nature of light that causes diffraction and blurs the images out. The other one is the quantum mechanical nature of light, the fact that light is made up of photons, and in a low light situation you're just not getting enough photons to be able to accurately measure how much light is coming on each pixel. And we've talked about some of the things we can do about these, but they are very serious problems and sometimes you can't do very much about it. But briefly at the end I'd like to throw out a bit more of the physics that goes on, because there's a lot more cool physics that's limiting detectors. One thing we've assumed, for example, is that every photon that lands on our detector is recorded, and that is not the case. The detectors are typically charge-coupled devices, CCDs. If you look at an energy diagram, they have what's called a band gap. They're made of silicon, and you've got photons in the base state and an excited state, but they're not allowed, because of quantum mechanical reasons, to be at intermediate energy, so that's the energy. So when a photon comes in, what it can do is knock an electron up across this energy gap, leaving a hole behind and putting one electron here. And this electron is then attracted to an electrode and therefore measured. The charge that builds up during exposure is read out at the end. So if you actually look at the silicon, you'll see a bunch of electrodes on top, connected by conducting channels which can read out, and so when a photon lands somewhere, produces an electron hole pair, the electron is attracted to the nearest electrode and then read out at the end of the exposure. Now this has a lot of problems. One problem, for example, is the band gap energy here corresponds to a photon of wavelength of about 1.1 micrometers. What that means is, if you remember E equals h nu, when the frequency is lower than 1.1 microns, there's just not enough energy in a photon to produce an electron hole pair. This means that silicon-based CCDs are completely insensitive to most infrared radiation. They can see the very near infrared, but most of the thermal infrared, you can't do it. Not a problem for commercial phones, but it's a big problem for military applications and astronomical applications. The military in particular, infrared is very good for seeing hiding objects and for picking up rocket plumes and things like that. And you can't use silicon for that. You have to use more exotic semiconductors like indium antimonide and mercury cadmium telluride, which are also used by astronomers to observe at infrared wavelengths to see through interstellar dust. Another problem is that you're going to lose some of the photons that come in because they're going to hit all these electrodes along the top. One way to fix that is to flip your silicon over. So at the moment, an old-fashioned CCD has the electrodes on top. What you can do is turn the whole thing upside down and have the electrodes on the bottom, so they're not blocking any of the light. You have to make the silicon extremely thin, otherwise it's too far from where the photons come in. The photons come in at the top and produce the electron hole pair, it's too far to the electrode. So what you have to do is turn this over and then thin it down to it's only a few microns thick. But these are called back illuminated CCDs, and they are widely used nowadays in actual cameras because they get more sensitive. But even then there are more problems. One problem is that very long wavelength photons can often go right through the silicon at the other side without interacting with anything. On the other extreme, ultraviolet photons will often produce an electron hole pair right near the surface, and it won't get as far as the electrode, because there are typically imperfections inside your silicon, and so as the electron wanders all the way down towards the electrode, it'll get snaffled by some imperfection and never get it. And there are various things you can do. For example, you can put fluorescent coating on the surface here so that your ultraviolet photon comes in here and causes the coating to fluoresce and produces, say, 2 green photons, which are much better at penetrating down to where they're needed. And you can do various things with doping, so-called deep depletion devices, to allow the long wavelength photons to work through. But the net effect of this is that the efficiency varies with wavelength. It's typically quite low for ultraviolet, pretty good. Some modern detectors are up at around 99% efficient for green-yellow light, and then drops off to 0 by the time you get in the infrared. And this is a big problem, particularly for astronomers, as often these ultraviolet and these infrared wavelengths are the ones we're most interested in, and a lot of work goes into trying to make the curve look more like this. Another problem is, when you build up all the charge here, let's imagine you're doing an explosion. You want tens of thousands of electrons to beat down the photon noise. So all the electrons are accumulating at the electrode. But as you get more and more electrons at the electrode, of course, they're all negative charges, and like charges repel. So that can actually get such a negative charge that any more electrons actually don't want to go there but go somewhere else. You can get, so there's a limit to how much charge you can actually get, how many photons you can get in each pixel. This limits the dynamic range of an image. If you get too few photons in each pixel, you're going to get really grainy noise because of the photon noise. If you get too many, the electrons will start bleeding into adjacent pixels or just not get anywhere near an electron at all, which means that the whites in your image just get blanked out and the blacks become grainy. And this limits the dynamic range of your image, which is a big problem for many photographers. Another problem is thermal noise. If your camera is at room temperature, very often these atoms here are just jiggling around all by themselves because of the heat motion, and that can sometimes knock an electron up and produce an electron hole pair all by itself. This is what's called dark current. It means even with no light forming on things, you actually get patterns and signals in that. This is why astronomers cool your detectors down to cryogenic temperatures to stop this form of noise being a big issue. And there's also the electronics read noise. You've got to measure these incredibly small charges with high precision, and that's a formidable challenge for electronics. So there's a lot of issues going on here, but the most fundamental ones of all tend to be the ones we've talked about: photon noise and diffraction limit.